All right, so I think we've seen, again, two types of talk so far. We've seen kind of a very macro view and as well kind of a deep dive into the use of the technology. I'm going to talk about both, but I'm going to start with the macro view, so I will surely run out of time on the more micro view. But I did finally get my paper posted last night, so people can read more about it there. So just a level set to start with, I'm going to talk about machine learning, not AI, in this talk. And I'm going to focus mainly on the sort of biggest buckets of machine learning, the most popular, the ones that have really been disseminated very widely. Just to kind of fix ideas, supervised machine learning, the idea is that you have outcomes Y, you have features X, you have a bunch of independent observations, and your goal is to use X to predict Y on an independent test set. That independent test set should have the feature that the joint distribution of the X and Y should be the same. Basically, for machine learning methods to work, you need only two assumptions. The stability of the joint distribution across your training and test sets, as they're called, and second, the independent observations. Of course, there are machine learning methods that try to relax all of these assumptions and things like that, but this is the core case in like your first machine learning courses. This is what you would spend most of your time on. And so basically, you're just trying to do mu hat of x, the expectation of y given x equals x. And that's kind of what we thought we were doing a long time ago when we were running regressions before we kind of got a little bit smarter in thinking about what we want to do with regressions, and that we often wanted to do causal inference, and we often didn't want to just make these predictions. Now there's a bit of a resurgence and people coming back and saying, wow, now that we've gotten really good at making predictions, there's actually a lot of interesting things we could do with just predictions. And Sindel Mullainathan is the most articulate in summarizing all of that, so I recommend some of his. He has some nice papers and proceedings papers you can read. Unsupervised machine learning, you just have features X, and you either want to put them into groups or reduce the dimensionality of them. This, of course, has also been done for decades, like things like principal components analysis, a way to reduce the dimension of, say, survey data and so on. So actually, these fancy-dancy new machine learning methods are partly, like when you take a machine learning course, one thing you learn is principal components analysis. That's like the baby thing, and then you go on to the real stuff. And when you learn about prediction, you start out with OLS regression and logit models, and then you go on to the fancy real stuff. So if you read in the newspaper that a computer scientist discovered cats on YouTube, what that means is they took a bunch of pictures, they put them into groups, they didn't put any labels on them, there was no cats and dog labels, there were just a bunch of pixels, and there was groups, and it turns out the biggest group of images has cats in it. And so when you start looking at all those images, you see they're cats. And so afterwards, you say, oh, cluster number 1, 2, 3, the biggest cluster has cats. So I've done this, and this is something that is already happening at fairly large scale, so I don't really have to predict that it's going to happen. We're using it. It's very common in political science. Textual analysis is a huge subfield of political science now. It's being used in the humanities, also in economics. So I've used it. So actually, there was an earlier discussion about Google News. So two people in the room, Catherine Tucker and I, both wrote about Google News. One of the things I did in my analysis of Google News is I put all of the news into clusters, and then I saw which types of news people read more of or less of when Google News went away in Spain. So those are the types of things you can do, and you can use those in analyses. Another thing, I'm looking at geolocation data right now. So I feed into an algorithm just labels of places. This is place 1, 2, 3, place 2, 5, 6. Nothing about them. I see where people ping with their phones, and then I can try to figure out what are latent characteristics of those places, what are latent preferences for those places, and then try to put similar places together. It turns out, without giving any more information, I discovered Town and Country Shopping Center near Stanford. The most popular place in that cluster is Palo Alto High School. They get out at lunch every day, and they go across the street to the shopping mall, and most of the things on this list are things in the shopping mall where they all eat lunch. So you might ask, why would I want to do this exercise? And of course, if I was in machine learning, and I'm publishing with machine learning co-authors on this, the papers that they want to publish are like, we have a cool, fast algorithm that predicts better than all the ones before, and isn't that awesome? I'm helping them by saying, well, let's actually come up with a different objective. Let's use this and be able to make counterfactual predictions. What if a store closes, for example? What would happen then? And so these predictive models can be thought of as a baseline against which you would measure the effect of an intervention. But if I want to measure the effect of the intervention, when I look at people reading every article on the web, there's tens of thousands of them, are visiting all the places in the Bay Area, it's hard to describe what that impact is in a meaningful way. So this kind of dimension reduction can help us basically understand and summarize in meaningful ways the effects of counterfactual changes. So a novel feature for the machine learners is to say, hey, instead of trying to maximize goodness of fit, you should optimize for counterfactuals of interest. And if you have variation in your data, you can hold out data, like on days with price changes in my shopping data, or before and after stores close, and use that. If you have lots of those, you can use that to do your model selection, and that's different than what the ML people do. Okay, so basically the heart of my paper, I was about this kind of a weird topic in a way, like what's the impact of machine learning on economics? In some ways, this is not a very hard question for me, because in 2007, I was plopped down into a search engine by myself to try to, hired by the CEO to beat Google, with a bunch of engineers who didn't know any economics, didn't know anything about marketplaces or advertising or anything. They did know machine learning, and to try to make something happen. And this was actually like a life-altering experience for me. I saw the technology, I saw the A/B testing platform, I saw the engineering, I saw the machine learning, the metrics, and I was like, wow, this is going to change everything. And then I went back to my economics colleagues, and they ranged from, why did you sell out to do consulting, to pat on the head, you've lost it, to maybe polite listening. But nobody really gave me any positive feedback whatsoever that this was going to be an interesting thing, or that it was important, or that it mattered, or it would affect economics. And actually there was a lot of negativity around it, really. Like, oh, that's just prediction, or it's just this, or it's just that. I tried to sign up econometricians, even my husband, to work on problems in this area. He also would not listen to me. Fast forward a few years, now he's working part-time for Amazon, and he comes to me, he's like, oh, I want to talk about short-term to long-term metrics. Let's write a paper about surrogates. And I'm like, I did a project on that in 2009, and I couldn't get you to work on it. But sooner or later, a lot of people have now, what's great now is that, there was no way that a small group of people could ever tackle all of the different topics associated with this. And so it's very exciting now that people have gotten all these different expertise, and everybody's now having their own experiences with search engines, with Uber, with Amazon, with eBay, with images, and so on, and now collectively we're getting to this area of very fast progress. But back in 2007 and 2008, I started really thinking hard about what the impact on economics was going to be. I actually started to start a research lab in New England, in addition to the work with Microsoft Business. And it was going to be computational social science, but they showed up with a bunch of algorithmic game theorists and a theoretical physicist to lead it. And I tried to convince them that empirical work and this new machine learning thing weren't just like bad science, but they were actually good science and really interesting. So over the course of a few years, we managed to tilt that, and now it's an awesomely successful lab with people like Matt Taddy were there, Greg Lewis, Marcus Mobius, and some of the best sociology, computational social scientists in the world, and some of the best machine learners in the world. And so in trying to get there, I had to think a lot about what was the infrastructure, what was going to be different, what would it take to make this successful, both from trying to understand the impact and measure the benefits of ML, as well as to be able to actually incorporate it into our research. So here are my predictions, and I've basically been working on trying to either do them myself, help make other people do them, incent other people to do them, lay the infrastructure for other people to do them, in my universities and other organizations for the last few years. So the first prediction is just adoption of off-the-shelf machine learning methods for their intended tasks, prediction, classification, and clustering, will become common and pervasive and really not a differentiating factor for PhD students. And that's already happened and is happening. It's just completely standard to use machine learning for text in computational social science, and that's gotten to be quite big. Economists are actually a little bit slow, but we're also starting to use it at scale. It's just not even something to comment on, or it's not something to worry about getting publication for. I think a more interesting thing, and I think Sundal Mullainathan has been a leader on writing a lot of conceptual papers about this, is that we have also extensions and modifications of prediction methods to account for considerations in terms of putting them into practice. So most real business problems or real policy problems are not actually straight prediction problems. I can predict which customers will churn, or which ones will click, or which restaurants will fail a health inspection, but that's not the same thing as knowing how to allocate resources. The people who click are not necessarily the ones for whom the advertisement is most effective. the people who are going to quit your platform and churn are not necessarily the ones where it's most effective to give them a call and try to get them to stay. Some of them will quit anyways. So the causal inference problem is different than the prediction problem. The ML community has been very focused on, they had this huge hammer and like hitting every prediction nail out there, but it's only gotten them about 80 or 90% of the way there for most problems. And so we're seeing this interest both within computer science and within the social sciences in taking that next 10 to 20% steps to actually make this useful. And Matt and his team, he didn't talk about that, but at Microsoft Research and now in Microsoft Business, they're actually creating a new toolkit for causal inference and machine learning that can help businesses use these tools to make pricing decisions and so on. And a key point is that you can't do that off the shelf with the stuff that you learn in your PhD in machine learning at Stanford. You learn nothing in your PhD in machine learning at Stanford about how to set prices, how to evaluate ad effectiveness, or anything like that. Nothing. And I've talked to a lot of people, and I'm quite clear that they are backwards in their thinking as a result of their training on these topics. But they don't understand that either. So a few other things like fairness. Credit modeling, maybe it has restrictions from regulatory considerations. You can't use certain variables. We want to think about fairness in hiring. So in all of the different applications of machine learning, we're going to be thinking about other considerations. There's also considerations the models need to be interpretable, that people understand them. There's actually a lot of confusion about this in computer science and in machine learning, and things that seem clear to us from the way we've been trained in economics. Just as an example, if you think about running a regression with 10 x's that are important, is it easier or harder to interpret it if you pull out 3 of them that are correlated with the other 7? Well, it's certainly a simpler model, but it's not easier to interpret because now the 7 that are left are picking up the effects of the 3 that you pulled out in some complicated ways. And to actually understand what's left, you have to understand the full joint distribution of all the variables. So a model with less covariates in it looks simpler, but it might be misleadingly simpler. It might be interpretable, but it's actually misinterpretable. And because there's not a language for causality or omitted variables or things like that in the classic machine learning training, people get very confused about that. And there's like literatures about interpretable models that just don't really tackle these issues at all. But of course, then it's up to us then to really come up with better definitions of interpretability and define what does it mean. And of course, it's going to mean different things in different contexts. The third one, and this is one where I've been writing a lot of papers recently with a whole collection of co-authors, is the development of new econometric methods based on machine learning designed to solve traditional social science estimation tasks, e.g. causal inference. So machine learning has this feature that because it can be evaluated on a test set very easily, you don't need statistical theory. So if you think about it for a second, if all I'm trying to do is use x's to predict y, if I have an independent test set, I can see how well that model does. I don't need any theory. And in fact, the theory is trumped by the data because you actually can see for the particular data set, for its particular structure, how well did I do predicting. So theory is kind of irrelevant. And from a sociology of science perspective, I think this is one reason this area has advanced so quickly. It's like they have a great way to have horse races, and they're all racing to get a little better mean squared error, a little better predictive power. There's one agreed upon metric for success. Everything else can be a black box, and you just race to succeed. So that's very different than causal inference, where if your instrument doesn't work on a training set, it's also not going to work on a test set, and testing it out doesn't really help. And in fact, instrumental variables, if you think about it, if you do an OLS regression of quantity on price, you're going to get a high R squared. If you do an IV regression, your R squared is going to be about 0.001. And so, we are used to throwing away all the predictive power to focus on causal inference. So it's really a very different way of thinking about things. And that's basically what a couple of teams, including a team at MIT led by Victor Chernozikov, Bologna Hansen, and others. Our team actually, there's stuff coming out of Microsoft Research by Matt Taddy's team. A few teams are really exploiting this difference to do interesting new statistical science because there was a big hole left that we're there to fill. Another thing that I've emphasized, and I have a survey in the Journal of Economic Perspectives and a couple of papers and proceedings papers, that we're going to have increased emphasis on model robustness and other supplementary analysis to assess the credibility of studies. That's both because we can use machine learning to test out a lot of different models and look at robustness, also because we're operating in settings where there are lots and lots of exogenous changes. we're releasing new algorithms every week. We're doing 1,000 experiments a year. So we have lots of ways to test the credibility of our models in these high-frequency data sets. Adoption of these new methods by empiricists at large scale. So I ended up staying up all night last night finishing my paper, in part because I just couldn't believe it. 2 of my papers in this area together had more than 200 sites in the last year. And I actually was way behind from preparing my syllabus from my course last year. And they were all substantive applications of this stuff. So if you worry that, oh, people aren't going to adopt this, that's just totally wrong. It's adopting so fast, you just can't even read it. And that's just my stuff. And there's lots of other people's stuff, too. Revival of new lines of research in productivity and measurement. So if we can use satellites and train a model if I can do a survey of 1,000 households, train a model with satellite imagery, and come up with a household by household measure of poverty, if I can use Google Street View images and go back for the last 10 years and get street by street, house by house measure of safety and quality of life and housing value, I can do lots of different types of studies about urbanization, about the effects of very micro level interventions. So we're going to see a resurgence of the science of productivity and measurement. And of course, we've already seen some of that this morning from a different angle. New methods in the design and analysis of large administrative data sets, including merging these sources. So, I have panels of data where I'm spying on people's cell phones for a year at a time, and then I can put that together with other data and understand their demographics, and I can understand who shops where, and I can do all sorts of analyses about the impact of transportation improvements and so on, impact of the retail apocalypse. And that's by putting together different data sources. The Sloan Foundation has given us a nice grant at Stanford to try to prototype some of that, because all of this is very hard. That leads to another prediction increase in interdisciplinary research. So I have a lot of co-authors now in lots of different areas: management science and engineering, computer science, civil engineering, and transportation, because you just can't learn all of this as one person. And also you need larger teams to carry out this research. We have papers with 4, 5, 6 authors. The changes in the organization, dissemination, and funding of economic research. I have 2 postdocs and a pre-doc to keep all this going. That's expensive. So, things like the Sloan Foundation have been generous to me, but we can't do that for everybody. So we've put together things like these shared pre-doc models. This year we've got 26 pre-doctoral students at Stanford. It's a very diverse group, much more diverse than our incoming graduate students. They're getting trained for doctoral programs, learning about big data analysis, but also at the same time providing the level of intense research assistantship and continuity that's necessary to do this kind of research. But we're going to have, we made a shared model for junior faculty to try to help with the problem that the young people are going to have a hard time getting started in this business. But at the moment, the young people are the ones who are going to do the most interesting work, so we really need to make that happen. So we got that set up at Stanford. It's actually a special students category. We did a lot of work to get it going, and it's super exciting that it's being so successful. The economist as engineer is a concept started, I guess, by Bob Wilson in terms of market design, and expanded by the other leaders in market design like Paul and Al Roth. I think that's going to expand even further to all parts: education, public policy, urban economics, because we're all going to go out and interact with people digitally. We're going to provide people information. We're going to intervene. We're going to do high-frequency experiments and so on. There's going to be the design and implementation of digital experimentation, both one time. I think that's all of our conception. There's an A/B test. There's A/B. We look at the results. The place where this is going, and Matt alluded to it, and I'm doing some research in this area as well, is this ongoing online experimentation where you start with hundreds of choices and narrow them down. We don't actually need to know a good standard error on 200 different things. We actually just care about the best ones. And so we can learn dramatically faster, orders of magnitude faster, if we start by throwing out a bunch of different things and then adaptively learn what are best and focus all of our observations on the leading candidates. And so this is something where the theory has been out there. Google has some great tools for firms to do this. Steve Scott, who's worked with HAL, has this for regular bandits. The state of the art is contextual bandits or personalized bandits. So I'm going to learn a function mapping from your covariates to the best policy for you. That turns out to be a much harder problem. Machine learners have attacked it, but they have missed some key points about modeling because they're not used to thinking about causal inference. And so we're coming up with improvements by bringing together the machine learning with the causal inference. Basically, if I'm trying to do something personalized, every single person is different. And so when you come in and I allocate you to a treatment, you're going to affect the quality of my estimation for other people when they show up, because I'm going to have to extrapolate if I'm trying to do something that's personalized. Generally, then, when I think about coming back to teaching now, we're going to see increased use of data analysis in all levels of economics teaching. You know, we have 1,000 people taking the machine learning course at Stanford. This is becoming very common. Our kids are going to show up at econometrics not saying, what's data? They're going to come and say, oh, I learned that logit models were stupid, and you know, you should use a deep net. Why are you using all this old-fashioned stuff? And so we're going to need to understand their question and explain to them what they learned in class and what they didn't learn in class, and teach them the stuff they didn't learn in their machine learning class and how to use it in practice. And that's going to make our students at all levels super valuable, because there's going to be 1,000 people that took the cookbook machine learning, this is how you predict class, and maybe only 50 people coming out of Stanford that actually understand how to use data to make decisions. If they can understand both, they're going to have a lot of value. Because of that, these kind of cookbook people will start to get less differentiated in the marketplace, and I predict that we're all going to get sucked into those data science programs. They were started in the engineering school. They're going to realize that they will have more marketable and useful students if they bring in social scientists. As well, the computer scientists and engineers will teach themselves a lot of our stuff, and they're already starting to. And so the curricula will evolve from being purely engineering-based to being more problem-solving. And that'll increase the demand for economists generally, but also just change the way we teach, what we can expect. You know, all my kids learn coding starting at age 6. That's going to be the case for all the upper middle class kids that are coming to our top universities in 10 years. Our MBAs are going to show up having done summer camps and written video games, and you know, we're going to be doing different things with them. Finally, of course, the topic of this conference, there's going to be so many changes. I'm definitely in the camp that believes that there will be disruptive changes. That's what I see on the inside of firms. I talk to firms who are about to lay off a lot of workers and so on. And I think we do need to worry about this. That's my personal opinion. And so we're going to have a lot of research about the impact of AI and ML on the economy, as well as research about how to help workers transition and provide other public goods that help with the transition. Thank you.
Great. Thanks very much.
Let's wait for the slides to come up. So Susan started her remarks by saying it's difficult to prepare a talk on the impact of AI in economics. I'll start mine by saying it's difficult to prepare remarks on what Susan thinks the impact of AI on economics is going to be. The easy thing is to say I defer to Susan. And so with that in mind, what I thought I would do is focus a little bit on the impact of machine learning on research in economics, trying to highlight a couple of sort of practical ways that the adoption of machine learning might affect the way we do research in the short run, and in particular the way we do empirical research. So I'm going to start with a slide that's maybe a messier version of something, you know, Susan started with, and you know, we can't have, I guess, talks on ML without pictures of animals. But Susan distinguishes in her paper, of course, between the unsupervised and the supervised, where the unsupervised is we give you a bunch of stuff and the computer categorizes what's similar and what's different. The supervised ML is what looks more like the empirical work we're used to as economists. Here's a set of covariates, a bunch of X's that are used to predict an outcome that's, you know, that we call Y. This is, you know, we've seen this applied in a huge variety of contexts. And so some of the problems where we're seeing this look like the kind of problems and the kind of data we're used to seeing, sort of structured data, quantitative data. I might predict which employees or which customers are likely to churn or turn over, predicting, you know, fraudulent transactions, predicting when, you know, jet engines need to be maintained. Here the data kind of looks like what we're used to. And then there's all these other applications that have the same feature of using X's to predict Y's, but the X's don't look like the X's we used to work with. So obviously image recognition is one example, natural language processing, which is then used to do things like, and we've seen companies come through the Creative Destruction Lab doing this, predicting what documents are relevant, let's say, for a particular legal case, customer service or bots or things like Google Home, where I'm saying something and it's predicting what it is I want as an answer, and even things like diagnosing skin cancer or other types of cancer. One thing that's interesting, I think it's obvious but helpful to point out, is in this case is the data that goes in doesn't look like the data we're used to. We don't have columns, we don't have X's, we just give them, you know, we give the computer pictures and it turns those, or we give it, you know, text and turns it into a bunch of X's. But the things that come out is a variable, a y that we can work with. And that's going to be something I'm going to pick up on because that gives us new stuff to put into the kinds of empirical work that we've been doing for a long time. So reading through Susan's paper and as background, looking at Hal's paper from a few years ago in JP and Sendel's most recent paper, the three of them together, I think, point out a couple of very simple but helpful distinctions between supervised ML and the econometrics that we're more used to. Of course, ML is focused on predicting y hat, and in econometrics, we're usually estimating some sort of beta hat. As people talked about, we typically specify our empirical model in advance. With ML, we let the machine choose the model. We don't pre-specify it. ML's typically, using correlations. We're generally interested in causal inference. And as Susan pointed out, with prediction, of course, we're maximizing goodness of fit. And she had this in her paper, and she also said this. We often sacrifice goodness of fit to get the estimate that we want. As she said, when we do IV, we throw out, a huge amount of the predictive variation in some endogenous variable and exploit just that little bit that we think might be, quote unquote, clean or exogenous. So Susan had that slide with, I don't know, a dozen or so ways that ML may impact economics. I sort of listed 5 here, and I want to focus on the last 2 because I think the first 3 other people have talked about and are certainly more qualified to talk about. But just to go through them quickly, one way people are applying ML and is saying, there's always been a bunch of economic questions that were prediction questions, and now we have these new tools that may allow us to do prediction better. And of course, as we have these new tools, we start to get more interested in questions that are inherently prediction questions, and that's a great thing. The second is already, as Susan was saying, incorporating ML techniques for things like model selection, robustness checks, variable selection into the type of econometric work that we do. A third is, these prediction policy problems. We always think of policy problems as being about, the counterfactual. What if we did this instead? In fact, as Sendel and others have pointed out, there's a bunch of policy problems that are prediction problems. The 2 things that I want to talk about, this one actually has been alluded to this morning already, is can we use ML to give us new variables or data on things that were hard to measure before and incorporate it into the types of traditional econometric analysis that we do, maybe shedding light on things that were hard to measure before? And how do we think about machine learning as the data generating process? So, people have written about this, and in fact, there's been, I think, 3 or 4 examples this morning. But of course, we can take text. Text doesn't look like data. We don't know how to put text, long bits of text or documents or into regressions. But what ML does is take something like, in the case of my paper with Athey and Joshua, a tweet, or in the example that Steve gave us, an email communication or a review, and turn that into a variable, which might be the sentiment or the content. We've seen the same thing applied, of course, to newspaper content, which can then be turned into a variable called slant. The applications for this, it seems to be are, I don't know about endless, but there seem to be many, many possibilities. Scott talked this morning about categorizing 90 some odd thousand research papers into these three areas of AI. It seemed a bit ironic that you said you had someone do that by hand in the opening talk at the ML conference. That seemed like the perfect classification problem, but that's the kind of thing that could be done, obviously. So Steve talked about using data. Ginger and I were talking at the break about research she's doing on 10K filings. All of these things don't look like traditional data, but ML turns them into data. And so some of the things that I think are, people are doing this on patent applications. People have done this on online reviews. What can we learn from looking, all of us who are interested in organizational economics, at the content of contracts, for example, performance evaluations of employees, facial expressions, how I react when I'm watching an ad, court transcripts, emails. All of this gives us new data. A related way that we can use ML, I think, in our traditional analysis, is ML predicts stuff. And sometimes that stuff is something we'd like to include in our analysis, but we don't have data on. But if we have data on things that correlate with it, and if we have data on those correlates and the thing we're interested in another data set, we can actually predict the X's or the Y's that we're interested in using. And there are a number of good examples from some of the Glaser papers at how we might do this. Obviously, this is a more advanced version of just kind of imputing missing values. But there's examples, from predicting hygiene scores from Yelp reviews, having them at a much higher frequency than they'd actually be collected, or applying this where it's easy to get data, let's say on income in one setting, you find correlates of that, and then you can predict income somewhere else. Finally, something I was thinking about, so, I teach courses to MBAs, sort of on data analysis, a very intuitive introduction to correlation and causation and drawing inference from business data. And it seems now we have to start thinking about machine learning as our new data generating process. And so, the data we usually analyze, of course, comes from the real world. We care about how the data, was generated. And we think about things like, well, the observed price is the result of interaction of supply and demand. That's why I can't regress Q on P. Educational outcomes, the result of people making optimal decisions on human capital. That's why the returns to education are hard to estimate. Firm boundaries, the result of economizing on transaction costs. That's why it's hard to figure out the performance implications. So I think we have to ask, how will our empirical work be affected when the data we get as empirical researchers come from decisions made by AI or machine learning and not from the people, the agents that we're actually good at modeling? And so I see this potentially playing out in two ways. If we think about structural estimation and drawing on what we see in I/O a lot, people write down models. We take the models seriously. We write a model of discrete choice demand and a model of supply. And then we take the data we have and use it to estimate those models and uncover the parameters that we're interested in. If firms are not necessarily setting prices according to our model, but as many CEOs are probably telling you and telling me, I have an AI set my prices. I mean, I do work on airlines. That's what the airlines are telling me. If prices are being set by AIs, do I have to adjust the model that I'm writing down for price setting to account for how the AI is making decisions and to account for which of the firms in my data are using AI and which ones aren't? And I also wonder whether the AI is getting us closer to our model. We often get criticized as economists. We write down these complicated pricing models. Nobody solves pricing problems like that. Maybe the AI is better than the former, pricing manager. But if we're going to, in models where we take things seriously, do we need to model the process by which the decision is made by the AI? And finally, in reduced form work, we have this sort of, obviously, this is familiar to everybody from Angress and Pischke. We know the random assignment doesn't always occur in the real world, and that's why we have trouble with, causal inference. What we're used to doing as empirical researchers is we kind of reason or model the data generating process. It's the higher ability students who get MBAs. Firms advertise at Christmas and on TV shows where they're going to find the customers who like their products. Now that reasoning, I think, has to include the decisions made by the AIs. And that might actually exacerbate the selection problem because targeting is going to be that much more effective. So in the extreme, or maybe I think the best example is you go view something on Amazon, and then it follows you around the internet for days, right? I looked for a ping pong table, and now for the next week, everywhere I go, I see those ads for the ping pong table. Well, isn't that exacerbating sort of the selection bias term, because the sort of difference between me and the person who didn't see the ad in our underlying likelihood of purchase is large. Indeed, that's why I'm seeing the ad and they're not. And so I think we need to think about the ML and how it impacts the data we're seeing as researchers.
Okay, thank you, Mara. We'll go Joshua and then Larry.
So the one thing that struck me about the two talks in this session and how they relate to the first two is this issue of AI adoption. And the talks here have highlighted the role that economists might actually more uniquely play, not just in things that we traditionally think of economics, but in any AI or ML application at all. The critical part in Paul's talk, which he sort of had to, but I think he would have glossed over anyway, was the point at when he pointed out that the Vickery auction, even small errors were going to lead to these dire results. Nobody other than, I don't think anyone other than Paul would have been able to come up and work that out. But that was absolutely critical. And how the process by which he persuaded the entire team that they needed to think completely differently about this, is actually a microcosm of surely what we're going to see for any of these prediction problems being put into the decision-making process of organisations. So I think this is a micro, and Susan certainly expressed that same issue as well. So it's worth us thinking about our roles here.
Okay, thank you, Joshua. There's a lot of hands up here. I'll go Larry and Chad and Andrea.
Couple observations on Susan's very interesting paper. First, there is this question, which is really the focus of this conference and which Susan mentioned last, which is studying the impact of AI on the economy. It's a feature of the way economists reason. We're the profession that made up the concept of widget, precisely in order to suppress the idea that different firms produce different products, and we basically abstracted that to all be the same. What's kind of striking about economics is how little there is that names particular product types or particular technologies. I asked myself, what was the classic study of the impact of the automobile on the development of the American economy? And there probably is one, but I didn't know what it was, and I'm reasonably well read. And so I just think it's a feature of economics that the aspiration here is a little different than the way economists usually think. That most of what we have in economics is sort of, it's not about particular countries, it's about the principles of money and the principles of fiscal policy. It's not about particular products, it's about industries that are oligopolies. And so there's something different about what's being aspired to relative to what economists usually do. Second, and I probably know less than anyone else in this room about the details of these algorithms, but a strong reaction from a variety of life experiences making policy in the public sector and in the private sector. I never believe any result that is brought to me from a model unless somebody is able to explain to me in a clear way, this is the number we got on the back of the envelope. We got 7 on the back of the envelope, but there are 9 other effects, and when we put them into the model, the actual number is 5.3. I say fine. But unless somebody can get me into the ballpark with something that I can understand on the back of an envelope, I tune it out. Tune it 100% out. And so when I hear causation and conditional prediction being snuck back into this, and it's classic use is prediction. Well, that's fine, you predict and you do it out of sample and it works, that's great. But when it's being used to tell me how I should price something or what I should trade or how I should move some policy lever, I think that's going to be I think the effort to sort of elide that gulch is problematic. I think that's a very big gulch, in part because it's sort of the essence of these techniques that there's some non-transparency about what major aspects of the data are driving it. So I kind of have a feeling that that's going to be much more difficult. A lot of this, it feels to me, played out after the discovery of the VAR. After the vector autoregression was discovered, there was lots of excitement, and then there was kind of a conclusion that within its class, it sort of worked for prediction, and basically people worked themselves back to the conclusion that it wasn't any good at causation. And so I just think you need to have a lot of skepticism about the capacity to do policy things in this way. I'll stop there.
Thank you. Chad, Andrea?
So this is going to end up following what Larry said. The thing I kept thinking about throughout the presentation and the discussion is the Lucas critique after 40 years of Moore's Law. It's like we've gotten really good, much better anyways, at predicting the relationship between variables. Lucas critique says, well, if you try to exploit those, you might not get the results you expect because those are equilibrium relationships and there's a deeper model going on underneath. And you have to understand that to do these sort of policy manipulations and get it in the way you expect. I'll just make a comment and a question based on that idea. The comment is, we economists are really good at recognizing that logic now, in part because of the earlier debates, and that might be a big area where we add value to the use of machine learning across fields, as we understand, prediction is not always enough to do interventions and to understand counterfactual outcomes. And then the question is, and I don't know the answer, with these new tools, the more causally oriented AI stuff, is it still just the same logic that we know about causation and understanding the deeper relationships, or do we have to add logic to it? Do we sort of have it and we just have a new tool to apply it with, or is there something we need to add to our thinking along those lines?
Thanks, Chad. Maria? And followed by Hal.
So both Mara and Susan mentioned unsupervised machine learning, but then there wasn't much talk about it, and it's something that we are using more and more in economics. So topic modeling is huge because we get, in fields like organizational economics, media economics, we get this avalanche of unstructured data, language, behavior, stuff like that. And what we do is we reduce dimensionality. We use LDA and stuff like that to reduce dimensionality. I feel like we're doing that in a complete theoretical vacuum. So it's very unclear which methodology we should be using, what it means for what we do. And then afterwards, we use standard econometrics and standard identification issues. But it's, to me, I would very much welcome some econometricians thinking more carefully through what it is that we're doing and how should we do it in a careful way.
Thank you. Hal, followed by Rebecca.
Can you give me some time to respond, because there's a couple of
Yes.
questions there.
Sure, I'll leave time for you to respond.
I want to follow up on this point that Mara made about letting the machine choose the model. Why choose? Why choose a model? It's much better to look at ensemble estimation or model averaging, and then you get an understanding of the really important uncertainty, namely the model choice as opposed to the sampling uncertainty, which is trivial compared to the modeling uncertainty, which is the critical issue. And if you want to follow up on this, go download the paper from Google Research on the causal impact package, where we have a way to do causal inference with modeling uncertainty, or look at the papers on my website about BSTS, which is Bayesian Structural Time Series. And this will give you, I think, quite a different perspective on the problem.
Thanks, Hal. Rebecca, followed by Matt.
Susan, it feels to me that your paper is an example of our paper this morning, that is machine learning as a method of discovery in economics or method of innovation. And I have a question about data access. You mentioned earlier that you have it is possible that in some cases machine learning reinforces a short-term bias and a bias towards what can be measured. And I was reminded of Sendel's paper on does machine learning automate moral hazard and error? So how do we think about data access in our field? Some of the large firms have been extraordinarily generous in making data available, but usually my impression is in ways that might help them. Going to a large firm and saying, well, we think your use of these techniques might be making you much more short-term and much less how do we think about data access? So this is going back to our question about who owns data and the kinds of effects that might have on invention. I'd be very curious.
Thank you. So you can take all the questions at the end, Matt, followed by Manuel.
Okay, so on the notion that machine learning is bad at counterfactuals, which I fully agree with, this fits in the more general way that I'm thinking about AI. AI is where you combine structures of basic prediction tasks together to solve a more complicated problem. And as Mara pointed out, that's what economists and econometricians do. Think about a system of structural equations. You've set up a bunch of things, some of which you can then estimate with ordinary least squares through this painstaking process of kind of choosing your variables, limited to a very small set of data, et cetera, right? And so that's the way I think econometricians, or at least I work in this divide between economics and machine learning, and as a communication strategy, as a management strategy, I found it very useful to think about the economics, econometrics, providing the structure, and within that structure, you then have these clearly identified prediction tasks, and it's the prediction tasks that the machine learning thinks should be going forward. And just touching on what Paul said, which is important, which I didn't get to go to, is economists need to understand, if we're going to go through this way where we provide these structures and then prediction happens within them, we have to understand the stability of those systems that we're putting out. And sometimes, like in Paul's case, a heuristic is going to be more stable to errors in the machine learning pieces of the structure than perhaps the most theoretically appealing thing.
Okay, thanks. So Manuel, Eric, and Steve, they'll 30 seconds each.
Well, I've been doing a great deal of policy in the last few years and policy design, and I'm confused, I must say, because essentially, every time, you try to do policies, and in particular policies that are not marginal, that are not at the margin, are more radical, okay? Then clearly, you can't expect that the predictions will be from the existing data, regardless of the power of the machine learning, will give you answers. And you need more and more sophisticated thinking, right? Models and so forth. So the way I will think of it is that machine learning, I hope that it can give us more empirical base from which to formulate the models, as Al was saying, essentially, that will allow us to make a better policies and not to be a substitute for it.
So this comment actually builds on Joshua's, Manuel's, and Matt's comment that, as Joshua pointed out, Paul's brilliant insight about the Vickrey auction helped save that, but I would have thought most people aren't necessarily as smart as Paul in that, and it might not have happened. What would have happened otherwise? It probably would have run, and it might have led to some disastrous outcomes. And I think part of the lesson is, okay, we need to think harder about making the decisions right, but also I think we need to model that most of the time progress probably doesn't happen from people consciously getting it right up front. It comes from trial and error and error and error and error. And as the tools get more powerful, we're going to have more of, I think, this risk of instability and some very unexpected outcomes. So, in the morning we talked a little bit about the mean being higher, but I also think I can imagine the variance being higher, that there, especially if there's path dependence, I suspect we could have a lot more unanticipated outcomes as people try out some of these tools and they have 20x different outcomes than what they expected. So the policy implications are not just to try to come up with better prediction. I think net we may end up with worse prediction because of a red queen kind of thing, that everybody's doing this simultaneously. And we may want to think about structures that are more stable, that are more flexible, that are more quickly reactive as these things interact with each other.
Hey, Steve, and then Susan.
So it's in a similar theme. When Susan used the term, it grew so much because they don't need theory. There was an article in Wired magazine, I pulled it up, it's from 2008, where the title was "The End of Theory, the Data Deluge Makes the Scientific Method Obsolete." And as much as we're talking about here what AI could bring to economics, I think it's really important, and I think this is exactly in the spirit of what you said, Susan. We as economists have a lot to bring to AI to remind them that you can't do strategy or policy work without thinking about a model. Again, relating to Larry's point of, if you can't do a quick back-of-the-envelope cheap way, what's really going on there? And I think it's important that we hold that baton and push it quite forcefully.
Okay, thanks, Steve. Susan,
Sure.
3 minutes.
Yep. So let me start with the really big picture comment, because I think actually I took my task very seriously in terms of my presentation about the impact on economics, but I didn't actually talk so much about my own research, which is sort of trying to solve these problems. So I have about 12 statistics papers in the last 3 or 4 years that you can check out that try to systematically tackle a lot of these issues that were raised. And just some high-level themes, and you can read them in the paper as well. are, first of all, that most problems that are interesting for us can, if they're not pure prediction problems, you can really decouple them into the part of the problem where you need to really think about causal inference and the part of the problem where we don't really have a lot of prior knowledge and relationships are stable and things like that. So if I'm trying to look at the impact of a treatment, no magic, no machine learning magic could possibly make a model identified that's unidentified. Like, we have theorems about that with infinite data. So exactly what I teach my students at all levels, executives to PhDs, is that if you have a complicated model and people can't explain what's driving the causal inference, you should throw it out. But there are pieces of the model that you need to understand like that. There are other pieces where maybe you have no prior about the details of the interactions among a long tail of sort of descriptive variables, and you have reason to think that those variables have a stable relationship to your outcome. Those can either be things you want to control for, because if you don't control for them, you can't draw causal inference, or they can be things where you want to get heterogeneity. These are just characteristics of individuals, and I want to get heterogeneous treatment effects. So those are two buckets where we've brought together machine learning and causal inference. And basically the big idea is that you use the machine learning to do the part that your research assistant used to do with 1,000 different specifications, and you didn't tell anybody that you did that. You have an automated research assistant for the part where you don't really have economic structure or whatever, and you use the data to do that part. But then it's back to all of our same old issues and problems with the causal part. But some things that are different now are that we have lots of experiments, we have repeated experiments, and so we can actually see whether some of these things are working. Another big thing that I try to, again, in this theme that economists are important, I try to really explain to executives, there are contexts where your machine learning guys are going to tell you, oh, let me keep tinkering with the model, I'll just fix it tomorrow. If you're doing credit scoring, you can't do that. You have to keep your credit model the same, because every time you change it, you change the adverse selection problem, and you're never going to keep up with yourself. If you're doing health stuff, you can't change your model every day. So we're training a bunch of people for an environment where in school they learn, oh, I'll just throw this all together and improve it, and it doesn't really matter if it's stable or anything else. But then when you go to a real policy or business context, all these other considerations come in. And so I've just re-emphasized that's what we're good at. That's what I view the research agenda as being, both from a managerial perspective as well as from a science perspective. And what's been really cool is that a bunch of us have been able to actually pull out these problems and make them really awesome statistics papers with great theorems, or really cool empirical papers demonstrating these phenomena. So we've been able to turn it into really interesting science. One other thing that Matt mentioned is these models, another way to think about it, these models are kind of semi-parametric. So we want to model the part that we need to model and then soak up the part that we don't. A few other quick things. Machine learning is a data generating process. It's something I think a lot about because I was designing the algorithms that created the data, and in search, we had that loop. So there is actually in some sense, that's a new methodological issue. There are machine learning, there's people who write papers about how to analyze logged data. And logged data is like data that's coming out of a search engine. And you'd think, oh, we understand the process that generated it, but the algorithms generating that logged data are not written down in a closed form, and they're constantly changing. So it's kind of this complicated thing where on the one hand, you created all the selection problems for your personalization algorithms, but on the other hand, you still have to use a model to estimate what you did because you can't even write down what you did, although you might know who was in which experimental treatment, and that's something that can be used. So I think it just basically, the bottom line is, yes, absolutely, these are just, prediction off the shelf can take you wildly astray. And so that's why I'm so passionate about getting us all involved to really make it better. And it's really interesting scientifically. Rebecca mentioned data access. That's actually something we're working on with the Sloan Foundation and others to try to model various forms of data access. One thing I tried to do at Microsoft is we had data that could be used to study things that were really unrelated to Microsoft's business interests, like news. So I wrote a lot of research papers about news using Microsoft data because they didn't care about news. So I think you can find these cases where data is available and there are research topics that are sort of orthogonal to the company's research, but then you can give them some benefits from using the data, and you can find something that creates gains for everyone. But it's absolutely also an ongoing thing. We need to figure out the right infrastructure, rules, guidelines, replicability, all of that, and model it so that people don't have to reinvent the wheel every time they try to work with one of these big data sets. And I spend a lot of time inventing wheels, so I really want to make it easier for other people, and I think collectively we'll all figure that out, over the next few years.